Hello students, welcome back. I am teaching you a course on circuits and systems, and in the today's lecture we will study about the fundamental of the Fourier series. Well, I hope you're all aware of the waveforms, and let me draw a simple waveform. Suppose you have a simple waveform. I draw here a simple sinusoidal waveform. Now this waveform, as you observe, is a periodic waveform of period, let us say a period t. This waveform is periodic. This waveform is periodic because we observe that f of x plus t is nothing but f of x. After this repetition time, that is at this particular place, the waveform again repeats itself. So we call such a waveform as a periodic waveform. And any waveform which does not follow this relationship will be a non-periodic. But in this case, it is a periodic waveform. The French mathematician Joseph Fourier, he showed that any periodic waveform, for that matter, if you say I have another, let's say this waveform, this also we say that it is a periodic waveform. Why? Because this waveform or symmetry is repeated. So this one wave, one period is repeated after this time t. So for any periodic waveform, the French mathematician Joseph Fourier showed that any periodic waveform can be represented by an infinite series of sinusoidal of harmonically related frequencies. So a fundamental frequency, let's say from this particular waveform, I have one wave of period t. So I can find out what this period t is, and with that one I can say what is the frequency. Frequency is nothing but 1 by t. So the fundamental frequency is the first harmonic of a waveform, and the other harmonics are the positive integer multiples of the fundamental frequencies. So if I say this f is nothing but the fundamental frequency, then the other harmonics of this fundamental frequency can be 2 times of f. So if you say frequency is suppose 50 hertz, then its second harmonic will be 2 times of f is equal to a frequency of 100 hertz. That means within the same period, you will have twice this frequency or half the time. So I will have two waveforms. So this frequency is the second harmonic of this fundamental. So this is the second harmonic. So with this introduction, the French mathematician, he showed that any periodic waveform can be represented by an infinite series of the sinusoidals of harmonically related frequencies. So this statement is true only for the periodic waveforms. If the waveform is non-periodic, then the Fourier series is not applicable. We will come out with other forms, that is a Fourier transform for that matter. The Fourier series can be represented in the sinusoid as the sum of a series of sines and the cosine waves as f of t is equal to a0 plus summation of the infinite series, summation of I is equal to 1 to I is equal to n. So this n can go up to the infinity. I is equal to n followed by the coefficients, and let the say coefficient is a n cos of n omega t plus b n into sine of n omega t. So this is what the Fourier series is, wherein we can say the Fourier series for any signal, any periodic signal is represented as f of t is equal to a0 plus summation from I to n of an cos n omega t plus bn into sine omega t, where a0, so this a0, where a0 is the average, a0 is the average or the DC components, is the DC component. So with this one, now let us say, see, you need to find out what the value of a0, an and bn is. So how do you calculate? We'll see the detailed elaboration in the next class. But what this a0, an and bn is, a0 is equal to 1 by t, where t is the period. From here to here is the period. If you say this period is of 360, 0 to 2 pi, then I will say it is from 1 by 2 pi. Integral from 0 to t, whatever the period is of f of t, this particular signal f of t into dt. Then an, the value of an is equal to 2 by t integral from 0 to t of f of t into cos of n omega t into dt. Similarly, we can find out the value of the bn, which is nothing but 2 by t integral from 0 to t of f of t into sine of n omega t dt. So these are the important relationships, and let me mark them with the. So these three equations are very important equations for finding out the values of the constants a0, an and bn, and once you substitute it back into these places, we'll be able to write the complete Fourier series for the given signal ft. Then you find the applications. Where do you find the applications of the Fourier series? We find the applications of the Fourier series in number of applications, including your image compression, signal processing, etc. So we'll see the applications in the forthcoming lectures. So for time being, this is all in this lecture. So see you in the next lecture. Thank you.